Knowledge is
Alright.
man.
Okay, so this is actually so we're gonna have to make good use of our time because we only have the lesson time
Okay.
limited once a week, right? And I'm gonna start a research project. So this is
Project,
term four.
wow.
Okay.
Ramsey the numbers.
You guys know what the Ramsey number is?
Is it a different number system or is it actual numbers?
Okay, let me give you an example, okay?
I can't tell which.
So if you have six people, right?
Yes.
Okay.
Yeah.
You can always find three people that know each other or three people that don't know anyone within those
Yes,
two.
I've seen this problem before.
Okay, so basically it's like this. You have
I've seen this problem in math enrichment.
yeah.
This is a very weird problem.
Okay, it's for us it's not really a problem. I'm just gonna tell you this
This
solution.
is just like graph theory.
So basically if you have this is what we came up with in the junior class anyway. So if you have another way of saying
Okay, so if you connect
so if
one
you have
to
one guy,
five,
right, and you're connecting it to five people,
one
right?
to five. Yeah.
Either it's because there's five people, either it's gonna be three people is connected to or three people is not connected
Okay,
to.
so
Right? So let's assume
so
it's
we'll log this.
they're
It's
connected to three
connected.
people. Yeah.
Okay, well that can't be a triangle because then that would be bad. Oh yeah,
Okay,
no.
and now you look at these three people, yeah.
Okay, these three people, not all of them can be not connected because that would be three of them not connected. So one of them is what's connected with another. I'm confused. Yeah, a triangle would be formed if none of them were connected, but if one of them was connected, then a triangle would be formed with the first one.
Yeah. So if these three didn't have any edges between them, yeah,
Yeah.
then you would get them all three not knowing each other, right?
Yeah.
Which is the conclusion we wanted.
Yeah.
So to not have that, there needs to be an edge, right?
Yes.
So you put an edge here, for example, yeah.
Yeah.
But now you have a triangle here, right?
Yeah.
So which means these three all know each other.
Yeah.
Which is
Wow.
the other conclusion. Okay.
Crazy.
So one of them has to be
Oh.
true. Okay.
Yeah, that makes sense.
Okay. And then we also have this diagram. You have a hexagon, right?
Yeah. Okay.
Yeah.
6.
And then we have all the non-adjacent connections are
Yeah.
like
Okay.
this, yeah?
Yeah. Go.
Actually, I can't remember if that's right or not. Is it right? So, sorry, I don't want a hexagon, I want a pentagon.
Okay.
Pentagon, yeah?
Yeah.
And I want all the non-adjacent connections to be erased, yeah?
Yeah. Yeah.
Yeah?
Yeah. Okay.
And so basically my claim is there's no triangle between any three vertices, and there's no dotted triangle between any three vertices, which is the same conclusion as
There's no triangle between any three vertices. Yeah.
there's no solid line triangle between any
that
three
means
vertices.
6 is the border,
Okay.
the boundary.
So that means 6 is the smallest number of people for which that conclusion can hold, right? Because 5 it can't hold anymore. Does that make sense?
Okay. Yeah.
Okay, so then how does this relate to Ramsey numbers? So we've just proved that Ramsey number. Okay, just give me a sec, it's charging. So Ramsey number 33, okay, is equal to 6.
What's 3, 3? What the heck?
So Ramsey number 33, okay, is the smallest number of vertices you can have in a graph, such that either you have three vertices completely connected,
Yeah.
or you have three vertices completely disconnected.
Wow.
Okay, or another way people think to like saying it these days is like, instead of having connected and not connected, you just have a complete graph with six vertices, and you color them in two different colors. So one is the one color is where the connections used to be, and the other color is where it used to be not connected, right?
Okay. So RAB equals RBA.
Yeah. So another way of saying this is that 6 is the minimum number of vertices you need for there to be guaranteed a K3 of one color or a K3 of another color.
Okay.
So if you color them red and blue to represent connected and disconnected, you know?
Okay, so it's just K something.
What does graph about? Is it assumed that every person knows at least one person?
No. It's any graph at all with six vertices, as long as there's no double edges and stuff. So it's a
So it's basically
simple graphs, yeah. Okay, so what? So basically, so another way of saying it, so Ramsey MN, okay, is the smallest number, let's say K, yeah, such that
Between
K vertex graph must have either a complete M or a totally disconnected N. Yeah? Does that make sense? Or another way of saying it is if you have a complete graph with K vertices
and
you color them in two different colors, the edges in two different colors, then it has to have a complete M vertex graph of one color or a complete N vertex graph of the other color. Yeah?
Yeah.
Yeah, so I mean, yeah. Okay, who does not understand the definition of Ramsey number now? This is the time to ask. Alright, Andy, your chance is over. Alright, so okay.
Now what?
Now what? So we just proved just then that R33 is 6, right? Okay. So the research project the juniors chose, well, you're the juniors as well. You're probably doing the same project. So R55 is actually not known.
Oh, what?
What? That's crazy.
Yeah, it's an unsolved problem.
Do we get to try and solve it?
What about
You could.
R4? What is that?
So actually, if you look at this table, I'm not sure how up to date it is. It actually tells you. So
R44 is 18.
Yeah, so R33 is 60.
Yeah.
So if you swap the numbers, it obviously doesn't change the Ramsey number because you can just take the complement of the graph. Yeah, you can just change the colors. Yeah.
It's a trivial symmetry because the diagonal.
So that's why all these bottom diagonal entries are missing. Okay. And you can see R44 is 18. Yeah.
Yeah.
That's amazing.
Okay, but R55 is not known. Okay.
What's R55?
But how's it not known?
Because we didn't figure it out.
No one figured it out.
And how did they figure it out?
Because they did.
Okay, so yesterday we discovered that as late as 2017, this number used to be 49. Okay.
Whoa.
And then 2017, there was some guy.
They decreased it by
There was
one.
some collaborators. One guy from ANU actually. Your dad's an alumni.
That's where my dad studied.
Isn't that what I just said? From ANU, got in the computer science department
They just computer
to do 2 trillion cases and eliminated 49.
Yeah, how do we not computer bash this?
Okay.
Just computer bash all the digits.
Technically,
You say just, which is very disrespectful. You see?
Can't we computer bash it?
You say just, but you couldn't do it.
Just computer bash it, bro.
Yeah, just get enough computing
Just do it,
power.
bro.
Bash it.
Just do it, bro.
Yeah. So then there's other things like, so if you look at the Electronic Journal of Combinatorics,
EJ.
there's a dynamic survey. Wait, where did it go? Dynamic survey.
Why do they have survey?
And it has a survey, so it helps people keep up to date with what's going on. In this dynamic survey, they have I don't know when this was last updated, 2021, see?
Yeah.
They have
They
that
have
43, 48 is still
the
current.
lower bounds.
They found 10, 12, and 11.
10, 12.
Yeah, so 310 is probably the closest to being known that's not known. See, it's between 40, it's either 40, 41, or 42.
Ooh.
Okay, so the other class picked R55 as a research project. Okay,
Hmm.
and we're gonna definitely do Ramsey as well. Okay,
Right.
so the question is what you want to focus on.
What do you want?
So we get to choose a number,
Wait,
basically.
so R
But isn't the bigger the harder?
R1015 is known.
Yeah.
10, 15.
It's just
Oh.
known.
No,
Oh,
they've
no,
only
maybe
found
they
the
don't.
lower
They don't
bound.
have an upper. Oh,
They've only found the lower bound.
I mean, obviously there's an upper bound,
Yeah.
Oh,
but
Because they have the lot.
It's probably too thick. Wait, actually no, they just straight up don't.
2 to the 48 cases.
No, it's actually 2 to the 48 choose 2. Because like it's kind of insane. So you know you're not gonna get it. So why can't they just computer bash it again?
Yeah, that's my question.
How many? Is that how many? 1, 2, 3. That's 281 trillion cases. Yeah.
Wait,
Isn't
no,
it
but
more?
it's 2 to the 48 choose 2. So that'll be like 48. Oh god, oh god.
I'm sure there's like
2 to the 48 to the 48 approximately.
I don't know. Like we could do something like we could use our brains to simplify the problem, you know,
Yes.
and then until we can get to a smaller number of cases, and then we can try and then computer bash it. Yeah. So actually, one of the privileges we have in this class is we have a lot of very savvy computer people in this class.
Alex.
Okay. Actually, and they're far more savvy at computer stuff than I am. Okay. So
I don't know what other good algorithms for finding complete graphs.
okay. I don't know. I was thinking like, what if? So for example, you know the R45 is 25, right?
Yeah.
Hmm.
So if you know R45 is 25, then what that means is every time you have 25 vertices, right? You can guarantee yourself 4 things that don't know each other at all,
Yeah.
right? And so
Okay.
okay, so you can actually get a whole bunch of those. Like even if it doesn't solve the problem, I think it would make it much easier to look at. And obviously people have probably tried something like it before. But yeah, so just because it's an unsolved problem and it's kind of famous does not necessarily mean it's hard, okay? But it does suggest certain things might not work. But it doesn't mean that we don't like just because it doesn't work, it doesn't mean we can't try them because if we don't attempt to even understand the problem at all and just skip everything and get to the solution, we're gonna have to either be like very lucky or very kind of probably ultimately it's just lucky, isn't it?
Yeah.
Okay, but as I said to the other class, we don't need to solve the problem. We just need to make some progress. We need to make some understanding. We need it as a good motivation to learn stuff that we need to learn anyway. Okay, so Ramsey theory.
Ramsey theory. What the heck?
Yeah, so maybe as a good motivation for this next chapter. So if you look at this graph theory book, right?
Okay.
All this
Chapter 9,
The
chapter 8.
Chinese book.
Chapter 8 is Ramsey theory. Okay?
Chinese comedy.
And theorem 1 was just R3 and 3 equals 6.
What is a logician?
Logic person.
What?
Okay, so theorem 1
Why?
was R3 3 equals 6, yeah? And if you want to see the video of that, we just read this book in the Monday class, yeah? So now we're up to theorem 2, okay?
What the heck?
But theorem 2 is a little bit...
What is that?
So theorem 3 is what Monday class is really going to get to next week, okay? And actually it depends on theorem 2. I'm not sure if they realized. But theorem Actually, maybe not theorem 2. Maybe it depends on theorem. Okay, what is theorem 2? Okay. Okay, so theorem 2 is so we're trying to generalize theorem 1 in a different way, okay? So theorem 1 is that if you color a complete 6-vertex graph with 2 colors, there has to be a triangle of one color or the other. Yeah?
Okay.
A full triangle of one color or the other. So what if you use more than one color, 2 colors, right? Should we do this on another video? Let's do this on another video.